Okay. Hi, we are group 15. So our final year project is performance evaluation of the Lora as a communication means for early earthquake warning system dissemination. So this is a collaboration project with Massey University, New Zealand. And first of all, I will give a brief introduction about the importance of the early earthquake warning system. So you can see these results. So we got from the database from the New Zealand. So there are, you can see the strong and weak earthquakes happen in recently. So in the right side, you can see the annual average of the earthquake from this table. So the earthquakes are not predictable thing. So we need to first detect the earthquake and send the message before earthquake reach. So that's the working of the early earthquake warning system. So if we, according to the World Bank records, if we can send the warning message of the 3 seconds, can reduce the death and injury rate by 14%. So that's the importance of the early earthquake warning system. So we are mainly focusing on the in our scope performance of the evaluation of the Lora as a communication method. So we are not dealing with the sensing and earthquake verification part. So when I talk about our final year task, so we need to send the warning message beyond to the 30 kilometers radius area before 10 seconds. So that's why, because the earthquake has two waves, secondary and primary wave. So primary wave is very speed, but it's not destructive. The thing is, secondary wave has most destructions, and its speed is 3 kilometers per second. So it needs 10 seconds to reach the 30 kilometers radius area. That's why we use 10 seconds as that our task. Over to you.
So, key deliverables of our project is evaluating multi-hop network to minimize the latency, designing a broadcast LoRa mesh network, adapting an extended simulation tool to establish a broadcast mesh network, and finally, publishing a research paper on our work. So, let's move to the main concept of our project. There are 6 spreading factors of LoRa. Using the highest spreading factor, which means spreading factor 12, we can achieve highest distance but with high time delays. Our main concept is we can achieve the same distance to the highest spreading factor using lower spreading factors without with lower time delays. You can see the numerical values of that in these tables. So in these graphs, you can see if we use the highest spreading factor, we can't transmit our warning message before the secondary wave propagates. But if we use the lower spreading factors, we can transmit our warning message before earthquake waves propagates. So this is our selected device for our physical testings. This is Liligo Lora 32 version 2 model. Over to you.
Okay, this is the proposed communication architecture for our project. So you can, there are 2 different nodes basically. First one is end nodes. It's like a packet originators and the end nodes not forwarding nodes. So it's situated in houses. So other one is relay nodes. Relay nodes is like we can place in the specific areas, and it's forwarding the packets. So you can see this left side simulation. You can see the packets are forwarding in the middle relay nodes. So others are not forwarding. So you can see this architecture also. Our relay nodes are placed in a specific locations, but n nodes are randomized because the n nodes represent the houses. Okay, these are the modes of the packet. So you can see the format of the packets also. If you want to more interesting about this architecture, you can follow these graphs. Okay, when we talk about our physical testing, so first we did the our testing in the Marine Drive Colombo, checking the capacity of the LoRa and evaluate the link performance we send in the packets. We got the results as we expected, and the second we did the scale down version and tested the Farouk experiment in the bypass road Piliamdala. Finally, we created a mini architecture of our project in our university premises Moratoa, and you can see the packet originator point, the detection point, and the relay nodes and end node.
Thank you. Actually, in our project, simulation tool plays a vital role because with the restrictions we had in the number of team members and number of nodes, we had to do our physical tests. So we could have the capability to fine tune the parameters using the small scale physical test, and then we could apply them in the simulation tool to prove the proposed architecture for a large scale network. So after a considerable time of literature reviewing, we selected Flora as our simulation tool. Actually, Flora is basically designed for LoRaWAN networks. LoRaWAN means there are n nodes which connected to a gateway in the star topology. Actually, our proposed idea was mainly designed a mesh network, a broadcasting mesh network using two types of nodes called the N nodes and the relay nodes. So even though we selected Flora, we have to do few extensions like creating a downlink for a LoRa node. Actually, relay node is also a LoRa node. It's also a normal node which has the capability to broadcast packets. And then we created a downlink, and we did the basic parameter fine tuning. And these were the things we done with the simulator tool: the propagation model parameter tuning and the verification and physical test data verification. And we simulated a generalized earthquake early warning large scale simulation network testing. So we selected log normal shadowing model as the propagation model. Here there are three terms, and this is the stochastic shadowing part. It varies in a normal distribution with zero mean and standard deviation sigma. And then this is the deterministic path loss, and it depends with this path loss exponent value. And this is the path loss at the reference distance. Actually, this is the path loss when there is line of sight. So we determined it using a physical test in our university playground. It has the line of sight, and we found out the value as 96 in the distance of 188 meters. These are reference values for path loss, and we have done physical practicals in the Marine Drive and the bypass road Piliyandala. And this is a small scale test which was done in the bypass road Piliyandala. We used 2 dBm transmission power, and we sent packets from one location to another, and we captured the RSSI values. And using these RSSI values, we could found the variance or the standard deviation of the dataset, and it is the sigma value, and we know this mean is 0. And after that, we could calculate the gamma value because we know the in this equation we know this term, the path loss at the reference distance, and we know this distance d naught. This is 188, and this distance is the now the distance between these two nodes, and this gamma value is what we need to find, and we could get the path loss using these RSSI values. The mean value can be taken, the path loss. Actually, we know the transmission power 2 dBm, and we can capture the received power, and the gap between it, that is the path loss. And then, since we know all these things, we could calculate this gamma value, and that's how we calculate. And then we selected another spreading factor, and so we could there is the distance changes, and then we verify that our found gamma value and sigma value are correct for this environment, and it can be changed with for a different environment. For this scenario, we selected these values for our selected environment. Actually, we done our practical in this is a urban area, and it was like in the morning in office hours, so the shadowing was high at that when we are doing this physical test. So it is most likely a worst case scenario. And these are the relay nodes, or the these are the relay nodes. They are placed in a grid, so this separation can be taken, can be selected using our previously calculated gamma and sigma value. This is the maximum distance which can communicate between these two nodes, and these are placed randomly here. These are the N nodes. This one N node can connect to at least one relay node or multiple, so these can broadcast the packets. Over to you.
So, we can scale up our scale down test to 17 dBm using this equation that we derived using log normal shadowing model. You can see how these distances can be scaled up using this equation in this table. This is the recorded video of our simulation. You can see the N nodes in red antennas and our relay nodes in white antennas, and you can see the packet propagation paths in red lines.
Okay. So these are the simulation results we got from our simulation tool. So we simulated 25 iterations with randomized placed in the N nodes. We randomized the N nodes within 30 kilometers radius area to get a more generalized situation, because the N nodes will represent the houses. So that's why we randomized the N nodes within 30 kilometers radius area. So you can see clearly the spreading factor 8 and 9 got the best results of this experiment. So when we talk about the average unreached N nodes, it's 0. Also, the maximum time to take in the reached node is 2.5 seconds and the 4 seconds. So that means our expected performance evaluation is completed. So we require like a 10 seconds. So before 10 seconds, we chose the using the simulation results we can do with this project. The performance evaluation of the Lora as a early earthquake warning system is completed, and so these are so we got the significant performance for spreading factor 8 and 9. So we need to use spreading factor 8 and 9 for getting more performance result for our project. So you can see the time available for preparedness also showing. So for the S wave and P wave in this graph. And you can see the blind zone for the secondary waves detection. So left right is spreading factor for spreading factor 8. So you can see the clearly all the nodes. The red line shows the earthquake. So you can see the blue dots is like a means our nodes. So all the nodes are get the warning message before the early earthquake reach. So when we talk about the right side picture, spreading factor 12, the red lines cross the some nodes. That means some nodes are got the earthquake before reaching the early earthquake warning system. So that's why spreading factor, we talk about the spreading factor 8. Okay, this is the real simulation environment we prepared for the Wellington city for New Zealand. So you can see our messages are propagated through the red lines. So we get the results as we expected from this in this simulation. And yeah, that's concluded this our presentation, small presentation for our final year project Group 15. So, and also we want to mention we publish our research paper in the sensor medium. If you want to more like interesting about this project, you can contact Professor Dileeka and also Group 15 members. Yeah, that's it. Thank you.